Okay, today we're delighted to have our IAS distinguished lecture by Professor Tom KUECH from University of Wisconsin and Madison, and he's the director. I don't know what about currently, and the founding director of MERSAT, which is interdisciplinary material research center. That there are a number of this in the United States, and University of Wisconsin and Madison has one of them. And Professor Tom KUECH is got his degree, PhD degree from Caltech, and then he worked at the IBM Yorktown Research Center for 9 years before he moved to University of Wisconsin. He went home and in Madison, and he's the department head or chair, whatever, at the chemical engineering department twice, and he is well, his endowed chair's name is too long, so I'm not going to say the whole thing. Okay, and he's a member of the U.S. National Academy of Engineering, a fellow of the American Physical Society, and IEEE, and American Association for Advancement of Science. He has numerous awards internationally from Germany in the Crystal Growth Society, and he's the editor-in-chief of the Journal Crystal Growth, and he's for I don't know how many years, probably 20 years. So he's going to tell us about the new routes to the formation of a complex, structured, and metastable materials, and all kinds of new materials you can dream of. And he's going to tell us the fundamentals, the physics, and how you are going to make them. Tom?
Okay. As well as talk about the new materials that we're looking at. And so one of the things we're looking at is right now you can compute and calculate new materials that don't exist. And you can do that pretty well. And so the question is, why don't they exist? And then how do you make them exist? And that's kind of what we've been working on for a number of years. Yep. This one's not working. Yep. It's not talking to each other. Oh, there we go. Maybe that got us there. Okay, so first of all, does anyone know where Wisconsin is besides me? One person, okay. So this is where you are, okay? That's where I started a couple days ago. Went over the North Pole and came over here. So this is the University of Wisconsin. Madison is the capital of that state. It's a little north of Chicago, if you know where Chicago is. And the campus has 42,000 people. And it is a beautiful city. It's built on 2 lakes. Until about a month ago, that lake had about a half a meter of ice on it. It is a northern climate. This is the College of Engineering. I just want to point. I'll expand that out. You want to try a different one? Yeah. Made a nice noise. There we go. So if you look at this, that's the College of Engineering. I just blew it up. I wanted to point out the only office that has a light on is my office. And I didn't ask for that picture. So that's my office. We have a lot of students in the college. It's the largest school in the state. Has about $2 billion worth of research funding a year on campus. So we do a lot of work there. And some of the work we do in my lab. And so I'm in the Department of Chemical Engineering. I just wanted to point out we work on all sorts of materials, and I like to think of it along a length scales. And so we have about 18 faculty, and if you're interested in chemical engineering and want to go to grad school, I welcome your application to go to grad school there. So this is the advertisement part. So let's talk a little bit about what we do use in technology to find out how we make those things. So these are kind of normal things that we we use, you know, cell phone, laser pointer, laptops, GPS. But if we look inside, these things have components. And some of these are made by, can be made by solution printing, solidification. You know, if you look inside a laser pointer, it actually has a laser, driving a frequency doubler. And so this was grown by epitaxy. These crystals are grown by bulk crystal growth techniques. You look inside of a laptop, there's circuits, there's transparent conductors. I don't think anyone really uses graphene as a transparent conductor right now. That's probably aspirational. And liquid crystals, which are self-assembled, so it's also something that's near equilibrium. And then, you know, we have wide bandgap materials. So these are all kind of materials we use today. And most of what they have in common is they're often used in bulk or thin film form. That's kind of the major way that we use things. And we use processes that operate near thermodynamic equilibrium. We usually don't think about that. It can only be near because you can't have growth if it's at equilibrium. All those applications require extremely low defect densities, which means structural defects and chemical defects. And lastly, they have to be commercially viable. You know, if you're making these things, someone has to buy it and someone has to make money on it. So what would we like to use? Kind of what are the hot subjects? You know, if you look in, there's a lot of things we'd like to use that people are researching that aren't these kind of traditional things. In metal, there's all sorts of new metals. They're called high entropy metals. We can talk about that if you want. Nanostructured metals, conductive nanomaterials to replace metals, transparent conductors, finding a substitute for indium tin oxide, new nonlinear materials, new solar materials, new materials for catalysis and other applications, new polymers, and new semiconductors. And so one of the things these have in common is that we're investigating them, but also we have limited ways to make some of these things right now. So what we're going to look at is some of the opportunities and then how we're trying to address some of them. So the opportunities right now are in finding in advanced materials processing that underlie all these technologies is finding new materials and structures, new applications, integrating them, self-assembled systems, and then quantum devices. What isn't being researched as much, but is equally important, is doing new process development. How do we make these materials? We need new processes to do this. We also need to model those processes because we need to control them. And we usually, currently the industry standard is something called model predictive control, meaning you have to understand something about, have a physical model of the process, which means you develop new tools or new alternative chemical processing techniques. And these are all at the forefront right now of materials research. So for the last 3 years, I spent at the National Science Foundation, and these are the kind of things that, both in materials and processing, that they were trying to fund. And then also just how do we understand things at the nanoscale? So one of the themes is how do we make things? And most things that we make are near thermodynamic equilibrium. So let's just talk about that and refresh your memory. Thermodynamic equilibrium basically means that the free energy of the system, which is the enthalpy minus the entropy, is at a minimum. And so going from A to B, it goes through, eventually at equilibrium, it's going to rest here because it's the lowest entropy state, which is lowest energy state, which is a balance between the enthalpy, the bonds, and the entropy. And so most of them, if we go through, we're going to go through a few of these techniques and see how we use thermodynamic equilibrium to make these materials, and then how do we deviate from that to make new materials. So one of the problems that comes up is that if we're making materials, we're almost always making materials out of something, right? So you have a solution, and so that's one phase, and you actually want a medium or a phase, and you want to make another phase out of it, the thing that you want to make the device out of. And you can see here that if I want to make a material that has this is just silicon dioxide, and aluminum oxide, alumina. If I want to make a material that's homogeneous of an arbitrary composition, I can't do that. If I cool it down, eventually it'll make two types of compounds. But let's say I had and desired to have that as a homogeneous compound. If I did make it, it would be metastable in the sense that if I heat it up high enough and long enough, it would fall apart into those two phases. So what we really would like to do is be able to take arbitrary compositions and make the structure we want. But equilibrium prevents us from doing that. And it does that because if I try to make a mixture, I have basically we have free energy that has to be a minimum, and that mixture has some extra free energy associated with it, and that's a deviation from ideal behavior. That free energy of mixing is what causes the phase separation. So if I look at a phase diagram, this is just a model phase diagram of something that has a liquid, a homogeneous phase, and then breaks into two phases. And that could be what I just showed you before, where one is a silica-rich and one's an aluminum-rich film. So let's say we start with a composition at 50%. It will eventually, if you calculate the free energy, it has this bumps in it, and that's due to the enthalpy of mixing, or the free energy of mixing. Those endpoints correspond to these points on the phase diagram. So if I cool it down at equilibrium, it'll generate some of this and some of this. And as the temperature goes up, it'll move up these curves until eventually I get to a homogeneous composition. So basically it says the free energy of the system drives it to phase separate. That says at equilibrium, but it has to have a pathway to do that. So we're going to talk about those pathways, but let's just go back to these materials form. So I said that all the things that we're going to talk about either are going to be macroscopic crystals, thin epitaxial films, or we'd like to use nanomaterials. We don't use a lot of them. We structure materials on the nanoscale. And so macroscopic crystals can be meters long. If you look at a silicon crystal that they use to make IC circuits, those are 2 meters long, typically, a couple hundred kilograms. And the way we make these bulk materials is solidification or solution growth or vapor deposited films. We have a lot of vapor, CVD or chemical vapor deposition going on here. And nanomaterials are generally solution-based. And these things basically, if we look at them in terms of equilibrium, these are very near thermodynamic equilibrium. These are very, very, epitaxial growth is often said as way out of equilibrium, and it's actually, under most cases, it's very close to equilibrium. And then sometimes near equilibrium. So let's investigate this a little bit more. So this is the free energy of just silicon as a material. And so I can look at it as a gas, a liquid, a crystal, or amorphous. We use amorphous silicon for displays and things. And if I look way up at the melting point here, a lot of these, the liquid and the crystalline curves are at the same point. They have the same free energy. That means they're at equilibrium. And so when I make bulk silicon, I'm making it out of a liquid. And we're usually using a process by Jan Czochralski, who in either 1960 or 1918 wrote this paper called a new way to measure the speed of crystallization of metals. And this was the start of Czochralski crystal growth. It basically is directional solidification from a melt. He did it for metals, sodium and tin and a variety of other things. He actually died a fairly unhappy man later on. But if I look at that crystal growth system, I basically dip a seed into a liquid molten silicon, and I control the growth of the crystal by just controlling the heat removal at this interface. The rate of heat removal tells me how fast I can get the enthalpy of solidification or the latent heat of fusion out of the material. And so at that interface, it is at equilibrium. And I'm just pull it up a little bit and cool it off. So I have a little bit of what they call undercooling. And that undercooling is so small that this is basically at equilibrium. And I can calculate all the properties of the crystal based on equilibrium. Its defect density, the number of vacancies it has, the amount of oxygen it has, and so forth. But I still have problems with directional solidification. One of the things I would like to make is a crystal of silicon germanium. We use that in transistors. If I were to do the same thing, if I would start with a certain composition of liquid germanium silicon and started to solidify, it would actually solidify at a very, very different composition of silicon than the melt. Silicon by itself is homogeneous, so crystalline silicon comes out of a crystalline melt. But because of the phase diagram, this liquidus and solidus, if I start solidifying this, directionally solidifying it, I'll have a crystal that has a lot more silicon in than the liquid. And that's because the enthalpy of fusion, or the bond energies in silicon, are stronger, and so they'd like to come out of solution. That means that I pull more solution out of the liquid, so the liquid shifts composition, and the crystal that I'm making shifts composition. And you can see that as it goes from germanium to silicon as I pull the crystal. Now there's ways around this, or people have proposed ways around that by replenishing the amount of silicon in the melt and so forth, but none of those have really been technologically. So the fact that I can't use equilibrium techniques to make materials, even in the silicon world, arbitrarily, is why we started to use thin film formation. And the reason we use thin film formation is because I can have a constant compositional flux to the surface. It's not like I'm growing a crystal out of a constant volume, which was the pot of molten silicon. And the overall, it's an isothermal system typically. The overall system is highly out of equilibrium, but the surface may not be. And we'll show that. And the growth and properties are determined by the state of the growth surface. And this is going to be a recurring theme. What happens at the growth front is actually going to determine whether we can make some of these materials we can design. So epitaxial growth, or thin film formation, atoms come down from the vapor somehow, either as a chemical form or as an element. And so you have to say, what limits the growth? Is the growth limited by the arrival of these new atoms, or by the motion and kinetics of reaction of these nutrients, if it's a chemical, and its incorporation? So what's happening at this growth front will determine what kind of material you'll make. If it's very close to equilibrium, you'll be constrained to thermodynamic equilibrium compositions. So what kind of time scales? How do we look at that? If you're near equilibrium, so let's say a typical epitaxial growth rate is about a micron an hour, which means the time to grow one monolayer is about a half a second. Right, so this is in a CVD system. If I look at how atoms diffuse on the surface, and let's say I have an atom come down, for it to find the right spot, it's going to move around on the surface and then find a location that it has the lowest energy. Let's say it has to move on the order of a nanometer to do that. That's 5 to 10 atomic sites, depending on the size of the crystal. And a typical temperature is 600. The surface diffusion coefficient is 10 to the minus 12 to 10 to the minus 13. So the time it spends looking for the right kind of spot to sit in is a few milliseconds. So an atom comes down, and within a few milliseconds, it'll find the right spot at these temperatures. On the other hand, another atom won't come by for another factor of about 1,000. So the number of atoms being added is very small compared to the amount of time, or is very long compared to the time it takes for an atom to actually react and incorporate. So we have two big length scales. Atoms are coming down, and they have to find the right spot. That arrival rate is very small compared to how fast the atoms are moving. So all the atoms find the right spot, generally. If I want to do something out of equilibrium, the time for one monolayer has to be much less, opposite of this, than the time for reaction and incorporation. And so we're going to go to non-equilibrium conditions in order to do that. And we can kind of see this in terms of a model of an epitaxial growth system. And this could also be of a solidification process, where I have the chemical potential, or the change in free energy with the chemical composition. And I look at this, and if it's near equilibrium, all the atoms will be used up at the surface and get incorporated. And so the growth rate is going to be proportional to the flux of atoms to the surface. And it's slow. And so I have very fast reactions. The atoms can move around on the surface compared to the slow arrival of new atoms. I can actually go to much lower temperatures, and now the incorporation of atoms actually takes much, much longer than the transport time of a new atom to the surface. And now the growth is going to be determined by these chemical and surface reactions. And I can manipulate those in ways that are advantageous. And we're going to show you two ways we can do that to create materials that aren't at equilibrium. So moving forward, typically compounds that are thermodynamically stable during synthesis are used. Silicon, gallium arsenide, are these nonlinear optic materials that are in this. We need highly structurally perfect materials so the growth rate is slow compared to transport. New materials and structures will often be those that are not absolutely thermodynamically stable, and non-equilibrium conditions are needed to make them. So we're going to show you two non-equilibrium ways we can make these materials. And again, this is motivated by the fact I can design materials in the computer and say, if I had this composition in this crystal structure, it would be an interesting material. Nature just doesn't provide it. So that's shown here. With the advent of both new technological needs and computational methods, design of materials to fit specific needs has been developed. Probably the biggest success of this is the cathode in a lithium-ion battery, lithium cobalt oxide, which was first discovered by computation. That is a stable compound, but it was discovered by computation. So we can often compute these properties of hypothetical materials, but often, typically, they're not stable if we look them up under ambient conditions, and will separate to multiple phases if given a kinetic pathway. So I can calculate these things. I can say, if I had this material, it would be really good, but often I can't make it because it's not thermodynamically stable. So let's look at why we'd like to do this. So if I look at the semiconductor technology, and this is a typical graph that's used. This is the band gap energy, the characteristic energy of the system versus the lattice parameter. And these are all the common binary and elemental semiconductors. And these are those bulk crystals that I could grow, and I can use these for epitaxy. So the things that I generally use are those that lie on these lines because they have the same interatomic spacing as the compound that I'm wishing to grow. And so you see these lines here. Anything connecting these lines are things that we've made and are stable. And most of what's inside these shaded areas we use technologically and are stable. But there's actually regions in here that are not miscible. So this actually, if I look at this, I could make a lot of combinations of these materials. Instead of just binaries, I could make ternaries, and we use those. I can make, for instance, along one of these lines, I can make gallium, indium arsenide. And I can change their properties by changing composition. I could change both, if I made gallium, indium arsenide phosphide, I actually can change both lattice parameter and band gap independently. So every time I add an element, I get a degree of freedom in designing the material. So one way of looking at this is that this actually is a huge compositional space. And so one thing I'd like to do is say, I could compute an arbitrary combination of indium, gallium, for example, indium, gallium, and aluminum, arsenic, nitrogen, arsenic, phosphorus, antimony, and find a composition somewhere in this compositional region, and it could have an interesting property. And the question is, if I wanted that, could I make it? And the answer generally is no. So we can actually expand into some of these ranges by controlling their formation kinetics and not using processes that are at thermodynamic equilibrium. I know we can predict their properties, and we can also exploit, so what we can do is exploit the surface physical and chemical kinetics to form them. And I'll give you an example of two ways we do this, one by changing the chemistry and one by changing out of the gas phase and one by controlling things out of the solid phase. So how to create these new materials which do not want to form? Well, we're going to control the surface kinetics for incorporation of atoms. And that means reducing or suspending mass transport to a great extent. And we do this through low temperatures and control of the chemical and physical structure. So what does this mean? It means that if I want to keep things from phase separating, I have to say, where is that going to happen? If I actually made the material, so let's say I wanted to make some compound that was in that phase diagram, semiconductor, and it is thermodynamically unstable. Let's say I could make it, all right? Let's say I made it and it was the right crystal structure and right composition. For it to fall apart, for it to phase separate, to reach equilibrium, things have to diffuse inside the solid. And phase separation after I make it, so if I could make it, it only can fall apart through solid state diffusion, which is incredibly slow near room temperature. You know, atoms don't move around inside solids very easily. And so if I could make it, it actually is stable and usable. So the trick is, how do I put the atoms together in the right structure? Because once I do that, even though it wants to fall apart, it has no kinetic pathway that's viable. So phase separation actually only can happen at a surface or an interface during growth. And that's dependent on the temperature, the flux, the structure of the surface, what's absorbed on it. And because on the surface, atoms can move a great distance at high temperature. So if I have a flux coming down of things that want to form an A and a B, they don't want to make a mixture. The atoms of A have to go to one side, the atoms of B have to go to another side. That means they have to diffuse on a surface. So if I stop that diffusion, the compound can form and A and B won't separate. And so I control, that's called mass transport. The atoms are moving, the mass is transporting over the surface. And so the trick that we're going to use is different means to suspend mass transport at the surface. So if the atoms come down and don't move around, they can't phase separate into different types of materials. So we're going to look at two types of ways of doing this. One is metastable semiconductors, one is a semiconductor, and one is an oxide. And we'll use two different ways of doing this. So first, let's look at an immiscible semiconductor. And the one that I'm interested in is gallium arsenide and bismuth. So bismuth is a big atom. If I put it into gallium arsenide, it actually could be a useful material. But this is the solubility of bismuth and gallium arsenide. And you can see here it's very, very small. It's 1 part in 1,000 or 10,000. If I actually make it an epitaxial system and it becomes strained to the substrate, meaning that the crystal doesn't have exactly the same lattice parameter, I actually can incorporate more bismuth into it. And actually, if I force it to decompose by forming gallium bismuth instead of bismuth metal, I actually get a fairly high solubility. And the reason for this is that strain is a thermodynamic energy term, and it's stabilizing this structure because it does not want to form this coherently strained material. So if I look at gallium arsenide bismuth by itself, it actually has very, very little I can get very little bismuth into the system. If I get about 10% bismuth into gallium arsenide, I can make a laser that probably has no, for those who work on lasers, Auger recombination, meaning it would be very, very efficient lasers. And that's because of the band structure, which we can compute. And this thermodynamics was computed using DFT. So epitaxial strain and how it decomposes can dramatically alter the solubility. So how do we do this? So we're going to do this by metal organic vapor phase epitaxy. And all this means is that I'm going to take some chemicals, run them over a hot surface, and have them react. And what's happening at the surface is going to dictate whether or not I can make this material. So the chemicals that I'm going to use are something called trimethylgallium. So I want to make gallium arsenide bismuth. But bismuth does not want to incorporate. So if I do this at high temperatures, so it's close to thermodynamic equilibrium, I'll get gallium arsenide and I'll get drops of bismuth on the surface. On the other hand, if I do it at low temperatures I actually can get some bismuth into the material. And the reason, and there's for a variety of reasons. The bismuth has no pathway, cannot diffuse on the surface at low temperatures to find another bismuth atom to start forming that metal droplet. So it has to go into the crystal. So I basically use low temperatures to minimize surface diffusion. But there's more than that going on. So what's shown here is a graph. And what's this shown is that while I'm growing, so let's say I put this, and this into the reactor to grow this compound. And I'll get a certain amount of bismuth into it. And as I'm growing, so this is growth time, so I start the reaction. and it's growing the film, and it's depositing and depositing. And what happens is after a very short period of time, even though I have a flux of reactants into the system, it doesn't grow anymore. It stops growing. All right, so it's going into the system, but it's not growing. And so but I'm also getting in orders of magnitude more bismuth into the film, at least into what I grew. So the observation that you should remember is that I can start growing a film and it incorporates lots of bismuth well above what it's supposed to have, but then it stops growing, even though it's still in that reactive environment. So the question is what's happening and how we can use that. So in order to investigate that, what we did is we grew a sample where we just put bismuth in the system, out of the system, in the system, out of the system in the vapor phase, and then grew a layer that had no bismuth in the reactor. And we saw something very unusual. So you can see these are the layers with bismuth in it, and bright here means bismuth. And so while I'm putting bismuth into the system, you can see I get bright, bright, bright. This is using transmission electron microscopy. But also when I stop putting bismuth into the system, so there's no trimethyl bismuth flowing into the reactor, all of a sudden I get lots of bismuth into the crystal. And the reason for that is because the bismuth actually was riding on the surface as a monolayer. And then all the growth was going through that bismuth layer. So the question is, how do I modify that? And then it actually stops growing. So the clue that bismuth incorporates from bismuth accumulated on the surface rather than directly from the flux. So that is something happening on the surface chemistry. And so we can look at this in more detail. So this is transmission electron micrograph. Here's where we're growing the compound, and all the bismuth gets incorporated after I stop. So the question is, why does bismuth go into the crystal when I don't have bismuth in the system? And when I have it in the system, why doesn't it incorporate? So it's actually the reverse of what I'd expect. And so while I'm growing, there's bismuth riding on the surface. And when I stop putting bismuth in the system, that bismuth gets incorporated into the crystal. I should also point out that once it's in the crystal, it stays there, and we can make devices out of this once we get it homogeneous. So we wanted to understand that in a little more detail, and so we use other techniques to look at that. One of them is atom probe tomography. And this is kind of a newer technique, which is actually quite exciting. And what it does is that you take and make a needle out of the material. So we have that film, and we use a focused ion beam to make a very, very sharp little needle of the material. And then we put it under a very, very high field, 10 to 50 volts per nanometer here. So we have this is grounded, and you have a big field here. And when I pulse this with a high voltage pulse, one atom will come off on average. Right? Actually, one atom will come off every 100 pulses. And so I'm pulsing this at hundreds of kilohertz, and every once in a while, an atom gets ripped off of the surface under that high field. And when that atom gets ripped off, it follows the field line all the way through and hits a detector. And so I can calculate the time it takes to go from here to here. That time will depend on the mass of the atom. So actually I can tell what atom that is. I can tell if it's an arsenic atom or a gallium atom. And since it's following a field line and I know where that is, where it hits this detector tells me where it came from this sample. So I'm pulling the atoms off one by one. I know which atom I'm pulling off and where it came from. Which means I can decompose this tip one atom at a time and reconstruct it in a computer to actually see where all the atoms are inside that crystal. And if I do that, you get something that looks like this. And so this is that tip, and you can see where the bismuth is and where the gallium and arsenic are. And we can use this to analyze to say what is happening inside the material. So if I have a material that wants to phase separate, one of the things I want to know is, has that started? Are there more bismuth near other bismuths than not? And we can analyze that, and we find out that the layer is homogeneous, meaning that even though it doesn't have any solubility, I put lots of bismuth in it, and it's a random alloy. So that is a metastable material. It doesn't want to have bismuth in it. It's a homogeneous alloy in this region, and we can analyze, and we have analyzed that. So why does this happen? Why can we get so much bismuth in this material? It's metastable. If I heat that way up to 700 degrees for a little while, all the bismuth will form droplets because it doesn't want to be in solution. And so let's look at this in a little more detail. If I have the growth of this material, I have these chemicals coming down, and right near the surface, I have all these chemical reactions. And lots of things happen in this system. It isn't just atoms coming down. I have lots of reactions. I have things diffusing down. They can react in the gas phase. They can attach. They can react on a surface. And then they have to leave. The byproducts have to leave, and I incorporate the film in the atom and leave behind an atom and incorporate in the film. So one of the things we wanted to do is say, one of the things that we notice is that I can grow some gallium arsenide bismuth, but then the growth rate stops. All right? It won't grow anymore until I stop trying to put bismuth in the system. So one of these, some chemical reaction is happening or some condition of the surface that allows us both to make a metastable alloy, but as well as controls the incorporation. So what we've did is we took every one of those reactions and either from the literature or we used density functional theory to look at the reaction rate. And then we combine these into a complete chemical model. And so there's probably about 20 to 30 relevant chemical reactions happening in the gas and the surface. And we can compute, some of those have been measured, a lot of them have been measured, but the ones that haven't been measured, particularly the ones on the surface, we can compute. And we can identify the key rate determining steps. And so one of the things that we find out is that while the film is growing, the film, if I'm using that trimethyl bismuth, so bismuth with methyl groups on it, it actually terminates the surface. The lowest energy, or this is the free energy, is when there's a bismuth, every bismuth atom is on the surface, and all the bismuth atoms have a methyl group on. And so that'll look something like, in a cartoon form, like this. All right, so that's what's happening during growth. And it's the methyl groups on the surface that keep any other reactions from happening. It forms like a Teflon on the surface. And so the rate limiting step is just removing these methyl groups. Now when I'm growing the film, I'm always coming in with trimethyl bismuth, and so it's always replenishing that. When I stop putting trimethyl bismuth in the film, there's lots of bismuth on the surface, and it starts growing and incorporating again. So the rate limiting step here was the removal of methyl groups. But the other thing that it did is that having these methyl groups on the surface kept atoms from diffusing around. And they did that because they took up surface sites. For an atom to move, it has to go from one site to another, to another, to another. With these methyl groups in here, sterically, it prevented those sites from being open for diffusion. So the bismuth atoms that came down stayed there because they were blocked from moving around. And so we went through and we calculated all these reactions, and these are rate constants associated for the bismuth, gallium, and arsenic with all the various basic reactions. And what you find is that the ones that have the longest rate constants was basically removing the methyl group from the bismuth atom. So the rate limiting step was removing methyl groups. So the way we've stabilized the surface is by absorbing a chemical species on it that prevented both surface diffusion that basically prevented surface diffusion and phase separation. So we can use chemical means and selective absorption on the surface to stabilize the surface and prevent phase separation and hence create a new alloy. So we took all those reactions and we actually could put that into a combined microkinetic model that said, can we predict as a function of the various parameters, and this is growth data from the literature, the various composition of bismuth and the growth rate of the material. And you find out that you can actually compute to a large degree many of these things. So if methyl groups was preventing the growth of the material, we tried triethyl bismuth, and that has different reactions. And what we found is that if we used triethyl bismuth, the growth rate kept going with time. And so it had no methyl groups on the surface, and so none of this was being blocked anymore. And so the growth rate continued. So the impediment to growth was removed, and the bismuth alloy formation was changed. So we also use this to create, so we can say, okay, if we understand the chemistry of the surface, that absorbing certain things on the surface keeps the material from phase separating, we calculated other new materials, gallium arsenide, phosphide, bismuth, and this material had not been grown before, or actually it hadn't been cited in the literature. But the bismuth and the phosphorus compensated. This is very small, this is very big. And so we should be able to get a lot of bismuth into the material by designing this. And then using what we know about the surface chemistry, keep it from phase separating. And using the ideas that we developed on the gallium arsenide bismuth with the surface chemistry, we actually did grow this material. These lines here is where it's lattice matched to gallium arsenide, and we could change the band gap over a wide range because we had so many degrees of freedom with the extra 2 elements in there. So, and we wanted to use this in a solar cell for a 1 eV cell in a multi-junction cell, and even though it was metastable, once you formed it, it behaved perfectly well, as predicted. If I heated it up to a very, very high temperature, eventually it would fall apart. So the other approach that we've used to make a metastable material is based on oxides. And this is something that we're working on now. It uses the idea that if I take an oxide, or a material, and here's my substrate, and I put down an amorphous material, all right? I can put down any composition I want, as long as it's amorphous. All right, because I deposit atoms at a very low temperature, and so I can form any composition I want here. And if I heat it up, what we hope would happen is that the material will reorder at the interface and start to develop epitaxial order. And so there's competing forces here. One is, do I nucleate a new phase in the bulk of this material? Does it grow from the surface? And just as we're using the limited surface mobility to create the metastable semiconductor alloy, at this interface here, there's very little mobility, atomic mobility, for atoms to move around. At best, some of these atoms can rotate around and maybe move 1 or 2 sites if you heat it up at low temperatures. And that's just enough for it to reorder. And so what we can do is deposit amorphous materials of arbitrary composition and then heat it up, and hopefully it will reorder. And so to do that, this is a process called solid phase epitaxy. It basically anneals the material at a low temperature. We also can deposit amorphous material into very complex geometries using atomic layer deposition. And so and this amorphous layer could be something that is metastable, in the sense that if I tried to make this by conventional techniques, it would phase separate. But if I put down the amorphous layer, let's say by sputtering or pulse laser deposition or atomic layer deposition, I can put down an arbitrary composition. And then if I heat that up, I can then use that to reordering to keep the material from phase separating. I can make a homogeneous alloy. So the way we make amorphous films is we sputter them or put PLD. You can put down arbitrary compositions. It depends on the target. And you can do that because the atoms come down and it's very, very cold, and they basically just stick. So it's like spray painting. And so I can make arbitrary compositions that, if it was crystalline, would have an interesting property. So the trick is I can make, by going from an amorphous material to a solid epitaxial material, I can use the limited mobility in the solid phase to create the epitaxial order. And so we can do that by sputtering. You can do this by atomic layer deposition as well. What's nice about atomic layer deposition is that it's very conformal in the sense that it can get into very small spaces. And so I can make amorphous films that have very, very unusual geometries to them. So going back to this particular diagram, we started out by looking at the transition from liquid to crystalline at equilibrium. But the amorphous material actually has a slightly higher free energy than the single crystal. And we use that difference in energy to derive the epitaxial growth. And we're going to use two key concepts. One is that it's going to be easier to reorient atoms onto an existing seed or to get epitaxial growth than it is to nucleate a whole new crystal. And so this actually works quite well. So we basically put down praseodymium aluminate. This is something that's used for making two-dimensional electron gases in complex oxides on strontium titanate. And we deposited it, this is by ALD, and you can see that this is an X-ray micrograph. It's an amorphous structure. So it is completely amorphous, and this is the same scan of the substrate and where there's no Bragg peak. And you can see that this signature here of the amorphous structure will be used to tell us whether it's crystallizing or not. If I take it and anneal it at 800 degrees for 3 hours, it becomes completely crystalline and epitaxial, and that's shown here in this area detector. Now what's significant is that the melting point for praseodymium aluminate is almost 2300 degrees centigrade. And we usually say you have to be at 2/3 of the melting point to get a lot of diffusion in the solid state. So we are very, very low. And hence, there's not a lot of solid state diffusion. All this allows us to do is to reorient maybe 1 or 2 atomic sites near that interface. Now we can do that. We studied this in a great detail using strontium titanate on single crystal strontium titanate. And so I'll walk you through this, and it basically says that if I take and deposit amorphous strontium titanate on a single crystal and heat it up, eventually this amorphous peak goes away because it becomes crystalline. If I do this on SiO2, so there's no epitaxial seed, it becomes polycrystalline eventually. But at the rate at which this amorphous peak goes away, or the rate of crystallization, is very different whether it's on an epitaxial or seeded substrate or whether it's on amorphous substrate, or it has to have homogeneous nucleation. And what's shown here is how fast it crystallizes, whether it's on an epitaxial substrate or on a single crystal substrate, or on an amorphous substrate. And you can see it takes 1,000 times longer, a factor of 10 to the third longer to nucleate on an amorphous substrate homogeneously than to epitaxially grow. So that means if I put an amorphous material on a single crystal substrate, it'll epitaxially regrow, and it'll grow a long distance. And that's what's shown here. So this is the vertical growth rate and the nucleation rate. And so what this says is that if I take from that data that I showed you, I can use this to say how far can I, if I had an epitaxial seed, how far can I regrow the material or form this single crystal material before it'll start forming other homogeneous crystallization and form other little crystallites. And you find that you can actually grow, depending on the temperature, we've done several microns of material. So the idea is that you have an amorphous layer and you start it to recrystallize or reorder through the amorphous film, and that'll reorder and recrystallize that whole amorphous layer. And that amorphous layer could be in very odd geometries. So conceptually it grows out from the seed into the amorphous material. It could actually grow up and over in a single crystal or up around corners. Because the crystallization front, this was amorphous, is going to move up and through. And so we can use this to actually make single crystal nanostructures inside materials that I formed using the amorphous material to begin with. And so we're using patterned substrates to integrate complex oxides in three-dimensional geometries. And the critical issue is just how fast does it grow off of the seed versus how fast does it start to nucleate a new crystal. So this allows us to do several things. One, the crystallization front is moving through the amorphous material, and if this amorphous material is of a metastate or of a composition that does not want to be thermodynamically stable, it has no kinetic pathway to decompose. And so I can recrystallize and form new types of metastable materials with this solid phase epitaxy. And we can do this by seeding it, by putting little seeds down and vertically and laterally growing out from those seeds. And so we can place these seeds anywhere on a substrate, coat it with amorphous material, and form single crystal complex oxides onto an existing substrate. And you can see that we use strontium ruthenate and strontium titanate crystals, and you can see little seeds where the crystal is growing out from there. So there's a variety of ways that you can use interface and surface kinetics to modify or form metastable materials into interesting structures. I just wanted to point out we have access to a synchrotron where we can do nano diffraction and actually look at the crystallization front as it's moving across in real time, and we're building that capability. So we can watch in diffraction the formation and the transition from the amorphous to single crystal material. And we've started doing some of that work, and you can see that the diffraction pattern this is on the order of a couple hundred nanometer beam size. We can get X-ray diffraction. We can see that there is some, in this particular case, there was some mosaic spread in the crystal. So we'll move on, just in the interest of time here, just summarize that. So I showed you two ways that we made metastable materials. One is by controlling the chemistry at the surface to keep atoms from moving around and phase separating. Once they form, if I stop them from transporting on the surface, they get incorporated in the film, and I can put in metastable compositions that way. In the case of solid phase epitaxy, the transition from amorphous to crystalline can only occur at the boundary between those two materials. And at that point, the amount of mass motion that can happen at low temperatures is very limited. It only can reorient the crystal to start that crystallization front or conversion from amorphous to single crystal. It can't nucleate a new crystallite. So I can actually recrystallize large volumes of material due to the lack of mass motion required for phase separation. So in both cases, both chemically and through the use of this sterically hindering it by having amorphous material there, I can provide limited mobility to an interface that allows me to actually form the new material. And this type of technique we found is broadly applicable to a large number of complex oxides. And so let me just summarize and answer any questions if there are any. That we can identify and determine new types of materials through computational methods. So that's how we got started on this. We could predict materials that were interesting, but they weren't thermodynamically stable, so how do we make them? Our approach is that we wanted to expand the approach to synthesizing these new materials and structures, which meant getting away from the traditional processing techniques which rely on things being close to thermodynamic equilibrium. This means you need to control kinetic processes, which is basically mass motion, and we suppress that mass motion by chemical means, by having things absorbed on a surface during chemical vapor deposition, or by having suppress the mass motion at an interface by having the surrounding amorphous material limit the amount of atomic mobility. And we can use that solid phase epitaxy approach to make new device geometries and interfaces. And so with that, I'll just say that this isn't just my work, but a lot of other students and postdocs, and this was done in what's called the Materials Engineering Research Center, which is an interdisciplinary center funded by the National Science Foundation. And with that, I'll take any questions you have.
So, in the first part, you grow this gallium bismuth, isn't it?
Gallium arsenide bismuth.
Bismuth.
Yeah. And we picked that because it was hard to get bismuth in the material.
Okay. You use it for junction cell, solar cell, isn't it? But there's many existing material at 1 EV which you can use while using this particular unusual or hard to get material.
Okay, so it depends on what material you'd like to use for 1 EV. This was potentially integratable in an epitaxial fashion with gallium arsenide. And so you could grow it monolithically, close to lattice match. And actually it has less strain for change in band gap than something like gallium arsenide nitride, which was another competing. So it's less strain, so you can grow thicker layers, which is what you'd want for the same amount of strain. It also has, for optical devices, the spin orbit band is quite deep. It's bigger than the band gap, and so that means you suppress Auger recombination. And so there was a big because of that fact, there was a large program in Europe looking at these kind of materials, but they're all metastable.
So thanks for your very informative seminar. I want to ask a question that you explained well that for the gallium arsenide bismuth growth that there is a phase segregation for the bismuth. But when you stop the bismuth source, so why the bismuth thickness is much larger than the underlayer bismuth segregation layer? Okay,
so what you saw is that we had layers, thin layers that we grew on and off, on and off. And then you saw a very thick layer, right, with bismuth. And so what was happening is that when we were growing those layers, those thin layers, bismuth started to accumulate on the surface. But it would stop reacting because it had all these methyl groups on top, all right? And so the gallium couldn't react. Soon as I stopped the bismuth source, there was no more source of methyl groups. And eventually they left. And now the gallium could start growing, and it started incorporating all the bismuth that was on the surface, which was probably a monolayer or two. And so it looks bright, but you can't tell the concentration from that. And so that monolayer or two, actually over that region, led to many percent bismuth in the film. And so that bright region, that thicker region, had more bismuth in it, and it was a little thicker because the chemistry on the surface allowed growth to continue and the bismuth to be incorporated. So while the bismuth was on, all the methyl groups were there, and no film could grow. As soon as they stopped the bismuth source, the bismuth that was sitting on the surface was now the source of bismuth and got incorporated into the film. And using that technique, you actually can get very high bismuth concentrations in the film, kind of pulsing it that way.
So you mean the residual bismuth source in the reacting chamber that will reduce on the surface of the, when you stop the bismuth source?
Well, so what's happening is that while the bismuth source is on, there is some bismuth still being deposited on the surface, all right? So in steady state, there's probably 1 or 2 monolayers of bismuth metal. It's not enough to form a drop, but it's absorbed on the surface. What keeps it from reacting and going into the film, or the film to grow, was the fact that on top of the bismuth, there were no open sites for the gallium to attach. And that was because of the methyl groups. Where do those methyl groups come from? They came from the bismuth source. It was trimethyl bismuth. And so while the bismuth was coming in, any methyl group that left was constantly being replenished. So there was always, whenever the bismuth was on the surface, it was always coated with methyl groups. When I stopped the bismuth source, those methyl groups came off and they were no longer replenished, and now growth can continue. And so what we showed is that if we stopped using a source of bismuth that had methyl groups in it, we had none of these problems. We used triethyl bismuth because those ethyl groups didn't stay on the surface, only the methyl groups did. And we showed that by calculation as well. All right? Yeah.
So, in your global crystals, you also have to concern about impurity incorporated.
Yeah.
Particularly for electronic devices. And impurity at surfaces, impurity in bulk, and vacancies and all that.
Yeah.
So how do you deal with that?
So, okay, so we showed two examples. First of all, the chemical impurities aren't really present in the
Not present.
in the oxide world, because the chemical impurities from the ALD probably would have been hydrogen, which you can, with a little bit of annealing, will leave, and carbon, but it's an oxide, so it's, the carbon basically oxidizes off. So the sources in the oxide case, putting down the film, the main contaminants would be hydrogen and the carbon basically forms carbon monoxide or carbon dioxide and leaves. In the gallium arsenide bismide, it really depends on the chemistry you use. So there's two issues. One, you get carbon into these films, as you do in all metal organic CVD cases to some degree. That is controllable by changing the growth conditions a little bit, as it is in gallium arsenide. But the bigger issue is that you can get things like bismuth antisites and other types of defects in there. Because we're constraining the mass motion on the surface, it doesn't necessarily able to find the optimal site to reside, which would be the anion site for the bismuth. In fact, if you let it roam around a lot, it would form bismuth metal. And so what happens to make these things usable is that once you get them made in the solid state, you can actually anneal them to fairly high temperatures. And that annealing, like it does in a lot of crystal growth systems, anneals out some of the point defects, which only typically have to move maybe a couple sites in order to get annihilated. So to make them useful for like a solar cell or a laser, all the materials have to be annealed to get rid of some of these point defects. But the main point is that I don't anneal it at a high enough temperature or long enough such that I can get phase separation, just enough to repair the damage in the crystal. It's kind of like ion implantation. You can anneal it some, right?
For organic material that I dealt with,
Yep.
they had none of these kind of problems.
Which material was that? Silicon.
Because there's so much problem in there, so many.
Mm-hmm.
So I mean, most of the organic cannot go into crystals anyway.
Well, anthracite, anthracene, and ruby.
Yeah, but small ones. So,
Yeah, right.
So I think I'll speak right away since I think my voice is loud enough.
Yeah.
So my question is going to be related to the second part. I think it's a bit closer to my material science background. I'm going to ask my questions out of my intuition. So you said the growth of the solid state growth of the amorphous layer into the crystalline phase doesn't involve the homogeneous recreation, meaning that you don't form polycrystalline phase.
Right.
But how about the, as Professor Zhang has mentioned, the bulk defects, vacancies or dislocations, does that exist more in the amorphous to solid state crystalline transition phase?
Well, it undoubtedly does. We haven't measured it because you have to have some signature. And so we've been mainly looking at the kinetics of this. I think there's a real difference between recrystallizing the oxides and recrystallizing or forming these semiconductors. Probably in the amorphous state, you can do X-ray, or at least some X-ray on that, or an X-AFS and things, and look at the coordination of the oxygen in the metal. And what probably happens is that in the oxide itself, it tends to form these tetrahedral units of oxygen. And those units don't have to move. What's probably happening is you're breaking a few oxygen metal bonds and it's just moving and rotating a little bit to reorder. And so that process itself probably doesn't create a lot of additional defects. Where the defects really come in, if you want to identify a route, is that there's a volume change from going from amorphous to crystalline. It's almost like a Kirkendall effect. And so what you need is either the film thin enough such that that volume, you have enough access to a free surface that the change in volume can be accommodated and relaxed. Or you need a geometry that automatically can accommodate the shrinkage of the thing. And so we see, and we measure it. We actually, even before it becomes crystalline, the amorphous material goes through several transformations. From being first as deposited, and it'll have a certain density. If you just anneal it at low temperatures, it'll actually densify but still be completely amorphous. And that's probably just a small change in, breaking of a few very high energy bonds but it's not enough to reorient, let's say, these octahedron. And then if you heat it up high enough, you get that reordering. So we do have an issue with volume loss. But if you have free surfaces or a geometry, you should be able to accommodate that.
Yeah, the volume change is actually going to be the second question I ask, especially on these complex geometry on the surface. When you have contraction, would that happen, say, at the corner a bit more than on a flat surface?
Well, in principle, you'd imagine it would, but, these things are, it depends on the nature of the bonding to the surface that it's on, right? So a typical thing that you can do is you can coat inside of channels. They do that with ALD all the time. In fact, for catalytic purposes, they take silicon nanotubes and coat them inside. And it's pretty amazing that it works down microns. It depends on how thick the layer is, what the geometry is, and what the bonding is to that amorphous substrate that will not seed the growth because it's an amorphous mold, if you want. But those are issues that we're still starting to look at. I think one of the major applications will be not odd geometries, but being able to make sharper interfaces than you probably can get with pulse laser deposition, which is how they make these things. And the reason for that is that you usually, when you do epitaxial growth, you usually get terraces and islands forming on the surface, which makes, if you put another layer on top, a rough interface. And a lot of the performance on these heterostructures and complex oxides, like you could take that praseodymium aluminate and strontium titanate, it'll have an electron gas at that interface. I can make the initial starting substrate of strontium titanate extremely planar. That interface between the amorphous material and the strontium titanate will be extremely planar, right? Because it's not mounting and that sort of stuff. So one of the things that we're looking for is whether the interfaces grown by solid phase epitaxy will actually be sharper than those grown by vapor phase deposition or some form of vapor phase PLD or such. And that would actually by itself have a tremendous impact because it limits the application of these types of complex oxides for electronic devices right now, the interface scattering.
The maximum amount of bismuth you got in there was what, 1.
Well, if we put in phosphorus, we can get in 10%.
10%.
Yeah.
So, yeah, for a while that people were trying to put nitrogen in the 3,5, the dilute nitride.
Yeah.
There was a long effort.
A long unsuccessful effort. Yeah.
Right,
Yeah.
but this is much harder.
Well, it sounds harder, but the internal strain due to the change in atomic size and the difference in electronegativity between nitrogen and arsenic and bismuth and arsenic, they're in opposite directions, but they're about the same. But what you get is you get twice as much motion in the band gap for equal amounts of strain by putting in bismuth than nitrogen, which is also insoluble in gallium arsenide, basically. So it's the same metastable problem, but actually if you use bismuth, the strain issue becomes less, and for an equal shift in band gap. And that's why if you just put in a little phosphorus, it doesn't shift the band gap tremendously, but it also provides a wider range for bismuth incorporation. And that's why you can shift the band gap down to almost an EV. We did it almost down to an EV, and we probably could have gone lower.
Also, a lot of people said that we want to make the gallium nitride system get all the way to the red if you can incorporate enough indium in there.
Yeah, or arsenic. Or arsenic.
Yes, but that's also been a very long, unsuccessful effort.
Well, that's because these have big miscibility gaps too.
Yes.
Right.
So is it a solvable problem? Because it's the people keep talking about it.
So, if you look at this, you can go in a little more detail. Basically, you can look where the miscibility gap is. And so that's the binodes of the system. You're also going to look where the spinoids are. Inside of that, it's inherently unstable, not just metastable, but unstable. And I think what happens is to get down to and you're at a high temperature in the gallium indium nitride, and you have a free surface. So atoms can move around, and indium has a huge surface diffusion coefficient and a high vapor pressure too, so it can come off and start forming clusters. So I think there's multiple issues in the indium gallium nitride thing. I think you're trying to push into the spinoids of the system, which, you know, can spontaneously decompose with any perturbation. You have high atomic mobility, which is exactly the opposite of what we have. And then you also have a high vapor pressure of one of the constituents at these temperatures. So you have vapor transport. You don't just have surface transport, you can have vapor transport to form clusters on that surface, because it can go into the boundary layer and move over, you know, across the surface. So you're working on a much harder system, actually.
You don't have a lot of indium docks.
Yeah.
You mentioned perovskite materials.
No, it's strontium titanate, right?
I mean, is it a metastable material that can never be mixed stable?
I'm sure.
I mean, it seems like they can make very high efficiencies, the solar cells, and it's somewhat crystalline material. I mean, what's your opinion?
Well, all the perovskites used for solar cells are stable materials.
Stable.
I think, yeah.
You think, or you're sure?
I'm pretty sure. I haven't really looked at it in detail, but I think they're pretty.
The way you look at it is half organic, half inorganic.
Oh, you're looking at. Oh, yeah. I don't know the stability of those. I think, once again, if you can make them, for them to decompose takes a lot more energy. You know, if you don't have a free surface, because you have to have some mass motion. I don't know. You know, most of those have fairly small amine groups in.
Yeah, very small.
And so, you know, and nitrogen forms pretty strong bonds, you know.
But it's tied to the.
But it's tied to the frame, you know, the lead whatever framework inside. So I don't know the answer to that one, but I also think though that's a system where there's a huge number of defects.
Right.
But, you know, it's ionic enough that those defects actually push the defect states get pushed towards the conduction and valence band, and so they're not like classic Shockley-Reed recombination centers like in gallium arsenide. And it's also like in gallium nitride. It's ionic enough that the surface states get pushed towards the band edges. And, you know, if you think of it, you know, if you just break a bond, it's going to be halfway between the bonding and anti-bonding sites, middle of the gap. If I turn up the ionicity, they just move. If you look at sodium chloride, they're within, you know, 10 millivolts of the surface states of the band edges. And so once you start moving those off of the center of the gap, you have to have a big activation energy for those things to start getting populated and depopulated, and they stop being recombination centers. And so the defects inside out on the surfaces, I think, are pretty benign in those materials, which is why I think they get high efficiency, even though the material is really cruddy material. So
they haven't yet demonstrated the stability. So
long term. But, you know, another issue with a lot of those materials is that you have, you know, in order for them to decompose, you have to have a bond breaking event somewhere, right? The bonds are not that strong. It's not like gallium arsenide or silicon, right? And what you can get is under higher radiance, you get enough photons in there that they can actually get absorbed by some of these defect sites and add to basically subtract from the activation energy to break that bond, and actually in the bulk under illumination cause bond breaking events. And they would see that in old gallium arsenide lasers, you know, where the photon field is huge, right, inside the laser. They'd see defects migrate around and point defects. And so these kind of radiation-enhanced defect generation and migration issues could be important.
The gallium nitride bond is several electron volts, but I think what is in the perovskite is less than 1
right.
electron volt.
And you're absorbing photons but you know, so that's the bond breaking. So that's you know, you still need an activation energy, right? And so what the photons do, and it doesn't happen very often, but you don't need it to happen once out of every 20 billion photons can get absorbed, excite the atom to a high enough state such that you're closer to the transition energy now, And then, so basically you need less thermal energy to break the bond because you have the photon absorbed by the defect or atom. And I think those kind of things happen in these materials as well, because we see it in more covalent materials. And that could actually add to the instability of these things under illumination, which is where they see it degrade.
We'll thank Professor KUECH again. For giving a very interesting talk. Thank you.
Thank you.